Our project is based on Faraday's law of electromagnetic induction. This law states that whenever the magnetic flux through a coil changes, an EMF is induced across it. The flux V is the magnetic field B multiplied by the coil area A. Faraday's law tells us the induced EMF equals minus N times the rate of change of flux, where N is the number of turns and the minus sign represents Lenz's law. Our objective is to demonstrate and verify three things: that a changing flux induces an EMF, that the EMF depends on the rate of flux change, and that more turns produce a larger EMF. This principle is the foundation of electrical generators, transformer, and induction charging.
For our method, we use MATLAB R2026A as our modern engineering tool to model Faraday's law numerically. We model the magnetic flux as a time-varying Gaussian pulse representing the magnet approaching, and then leaving the coil where flux equal electric field times area. The induced EMF was computed using Faraday's law, with the derivative evaluated numerically using the different function. Our procedure has 7 steps, which is define the coil and magnet parameters. N equals 100, B naught 0.5 Tesla, and area 0.01 meter squared. Build the flux pulse, compute the EMF, plot the results, compare different magnet speeds, sweep the number of turns, and finally verify against the exact analytical formula.
Here's our result. The first figure shows the magnetic flux through the coil, a smooth pulse that peaks at 1 second at about 5 times 10 to the minus 3 Webers, which equal B times A, is the rate of change of this curve that drives the induced EMF. The second figure overlays the flux in blue with the induced EMF in red. Notice the EMF crosses zero exactly where the flux peaks. At the instant, the flux is maximum but momentarily not changing, so dV over dt is 0. The EMF is largest where the flux changes fastest, not where the flux is highest. This directly confirms epsilon equal minus N dV dt. The EMF tracks the slope of the flux.
The third figure compares different magnet speed. A faster magnet produces taller, narrower EMF, about plus minus 4.8 volts for the fast case, versus plus minus 1.9 volt for the slow one. Importantly, the peak flux is identical in all three cases, only the speeds change. This confirms the EMF depends on the rate of flux change, not its magnitude. The fourth figure shows the peak EMF against number of turns. The result is a straight line. Doubling N doubles the EMF. As shown in the table, 50 turns give 1.5 volts, 100 turns give 3 volts, and so on. This confirms that the induced EMF is directly proportional to N, exactly as the law predicts.
Our discussion confirmed the three predictions of Faraday's law. The EMF is zero at peak flux and largest where the flux changes fastest. It depends on the rate of flux change, and it is directly proportional to N. We also recognize our limitation. Most importantly, because the model takes Faraday's law as a given input, it demonstrates internal consistency rather than providing independent experimental proof. There are no physical measurements against a real coil. The flux is modeled as an idealized Gaussian when a real magnetic field is more complex, and the numerical derivative introduces a tiny step error of around 0.0001 volts. In conclusion, we successfully modeled Faraday's law in MATLAB and verify its key prediction. Thank you for watching.